Hello everyone, here we have the problem solving for March 30th. As I've mentioned in the announcement section of the Brightspace shell, I'm going down from full 50-minute recorded lectures to focusing on the problem solving content, also assigned readings of the slides. I'm just finding that I don't really have the time or ability to do a 50-minute video, and based on the statistics I'm seeing, most of you don't have time to actually sit down and watch a 50-minute video. So do the assigned reading. Here we have the problem solving examples to work from, and then make sure you do your daily mastering chemistry assignment. Hopefully this will make this more accessible for everyone. This particular problem, we're focusing on Charles's law, how the volume of a gas will change with a change in temperature. The math here is not going to be very challenging, but the big thing we do have to realize, and the most important thing about solving these problems, is the temperatures have to be in Kelvin. It turns out gas behavior is such that it's at 0 Kelvin where gas molecules stop moving, and that's effectively the important aspect of all this. So we're going to do that. Let's take a look at what we've got. We've got a 48.3 milliliter sample of a gas in a cylinder is warmed from 22 degrees Celsius to 87 degrees Celsius. We need to know that 22 degrees Celsius is actually, if we add 273.15 to that, obviously that's going to be 295.15 Kelvin, and 87 degrees Celsius, if we add 273.15 to that, is going to give us, let's do some math in my head. I'm getting, what, 360.15 Kelvin? I should probably check that on my calculator just to be absolutely sure. So here we go. 87 plus 273.15. Oh, something's not right there. Let's try that again. 87 plus 273.15. Yep, 360.15. So that's good for us. We would have seen that Charles's law effectively says that V1 over T1 equals V2 over T2. Looks like we're looking to solve for a volume such that V2 will equal V1 multiplied by the ratio of T2 divided by T1. So what we see is, as the temperature, let's say, increases, if T1 is smaller than T2, we're going to see the volume increase, and that's Charles's law, because it turns out most everything expands, gets bigger when we heat it up. So this is going to be our 48.3 milliliters multiplied by our 360.15 Kelvin divided by our 295.15 Kelvin. And what we're going to see is the new volume of this gas is going to be 48.3 times 360.15 divided by 295.15. And so it looks like, and I'm going to keep 3 sig figs in here, even though there's really only 2 in those temperatures, because of course once we convert to Kelvin we see both of those temperatures have 3 before the decimal places start. So this is going to be 58.9 milliliters, because of course the Kelvin units cancel out there, leaving us with the milliliter units. That's the Charles's law aspect or question. We also have another question effectively dealing with Avogadro's law, how the volume of a gas will change with the number of moles of gas. Now this problem looks pretty intense, but at the end of the day, it's really not that difficult. Avogadro's law is effectively the idea that the volume of a gas divided by the number of moles of gas, if we keep the temperature and the pressure constant, and we change the number of moles of gas, we're going to see the volume change, and that should make sense. If I blow up a balloon with 1 breath, there's going to be a certain volume of balloon. If I use 2 breaths, doubling the number of moles of gas in there, obviously the volume should get twice as big. In this particular case, we start with some sort of amount of reactants, 0.120 moles. We start at some volume of 2.18 liters. After the chemical reaction is complete inside this balloon or cylinder with a movable piston, it turns out, we see that we've got about 5 times more gas, 0.621 moles of gaseous products. So what's the volume going to be? Well, it's 5 times more gas. It's going to be a volume that's about 5 times bigger. So I'm expecting an answer somewhere around, let's say, 10 to 15 liters at the end of this. So let's see if that's the case. My final volume, V2, should equal V1 times N2 over N1. So again, if we see the number of moles N2 is bigger than N1, we would expect the new volume to be bigger than the original volume. That's again 2.18 liters times our 0.621 moles over our original 0.120 moles. Of course, all those mole units cancel out. We're going to get an answer in liters, and that answer is going to be 2.18 times 0.621 divided by 0.120. And here we get an answer to the 3 sig figs we're allowed of 11.3 liters. Try that again, 11.3 liters, which again kind of fit our idea of 10 to 15 liters, so we seem to be doing okay. That's the problems of today's assigned reading. Obviously, our Mastering Chemistry assignment is probably going to be problems very similar to this. So go and work on those as soon as you're able, and we'll come back tomorrow with some more assigned reading and problem solving. Have a good one, everyone. I'll see you soon.